Hello everyone, a very good afternoon to all of you. Here we are gathered for a basic lecture on voltage multiplier circuits, which are primarily used for amplification of frequency supply voltages to any exception and recorded values. So here we will see about the types firstly, and then after, in detail, we will go into the workings of components, diodes, and see how the voltage amplification is being done. So here in first slide, we can see there are two types of voltage multiplier circuits mentioned, half wave and full wave. And also there is a advanced type voltage triplets and quadruplets. So let us begin with a half wave, see its merits and demerits, and how they are overcome in full wave voltage doubler circuits. Thereafter, we will move on to voltage multipliers and quadruplets. Now, as the name suggests, voltage is being multiplied. So, firstly, we have to see its utility. Now, voltage multiplication is surely done. In multiplication means we are receiving products in the multiplication twice, thrice, four times, five times, and so on. Now, let us take a basic circuit diagram of half-wave voltage multipliers. As we can see by the arrow, this is the primary arrangement, and there is a transformer-based system. Then there are two diodes arranged as such, and the two capacitors, and final output is being taken across output V naught. Now, since these circuits basically with the AC supply signals, so we will talk in terms of cycles, which are basically positive half cycle and negative half cycles. So let us move on to actual working of half wave voltage doublers and see how things are being done. So we are moving to the next slide. See, as the name suggests, working of half wave voltage doubler circuit. Now, as the first positive half cycle comes, for assumption or indicate positive and negative half cycles, in the positive half cycle, we have taken plus here and minus here. Secondary voltage Vm we have taken. Now, to understand its working, we have to see the behaviors of these diodes D1 and D2, and also capacitors C1 and C2. So as we see, the diode D1P type is connected to the positive terminal, and N type is connected to the negative terminal, which means diode 1 gets on by being forward bias. Here, for the sake of calculation, we are assuming that all diodes used are here in ideal conditions. So as I have clearly mentioned here, D1 gets on and D2 N type is connected to the plus of supply. So D2 gets reverse biased. So the only path for supply to move on is through Vm, C1 and D1. So D2 and C2 gets cut off from the system during the first positive half cycle. So D1 gets on, D2 gets off, capacitor C1 gets charged. As we know that current entry direction is taken to be positive and current leaving direction is taken to be negative. So applying basic KVL, we have obtained Vc1 equals to Vn. So after first positive half cycle, charge gets stored on capacitor C1 with given polarity. Now as we can clearly see, final output is taken across V0. So another cycle needs to be needed so that capacitor C2 gets charged. So moving on to next slide, we can see now during negative half cycle in comparison to the positive half cycle, voltage polarity has been inverted. Capacitor C1 has been already charged with plus on the left and negative on the right hand side. So this negative gets diode P1 reverse biased and this negative gets diode D2 forward biased. So D1 gets off from the system by having open circuit. So only path current can transfers is through minus Vm through C2, D2 and back. So to calculate the voltage across VC2, we are again applying KVL. Here we need to be careful that during applying KVL, we have already taken the care of the sign. So when we are placing the values of Vm, negative Vm already considers the negative half cycle. So we need not put again Vm magnitude as minus times Vm. This will falsify the system. So this bit care needs to be taken here. Now applying KVL, VC2 gets twice Vm, but output polarity is shown as this. So following this blue cycle, we can see that output and VC2 are related by this relation minus V0 minus VC2 equals 0. So ultimately gets V0 equals to minus 2. So we can see here that as the name suggests, a voltage doubler circuit gives the output as twice of the input on secondary side. But there is a limitation that output voltage we are obtaining here is of negative sign. So negative voltage are generally not preferred in the systems. So this drawback of the system has been overcome in another type of voltage doubler, which we term as full wave voltage doubler circuit. So moving on the next slide, this is the basic diagram of full wave voltage doubler circuit. Output V0 is taken across C1 and C2, and this is the basic arrangement. So now if you look at the bottom, first positive half cycle has come. Now as per connection done, this plus and negative polarity gets D1 forward bias and D2 reverse bias. So D2 gets cut off from the system, and so as capacitor C2. So capacitor C1 gets charged with the given polarity flowing through D1. Here again, we are taking diodes as ideal. So applying the basic KVL, we are obtaining VC1 equals to plus times Vm. So VC1 we have mentioned here equals to Vm and polarity as shown. This all happens when the positive half cycle of AC signal comes, means first positive half cycle. And so moving on to negative cycle. In reference to the positive half cycle, voltages are shown as this. Now capacitor C1, as this was connected diode D1, and due to the reverse in polarity, diode D1 gets reverse biased and diode D2 gets forward biased. So again, supply flows the current to the system and VC2 get charged with the given polarity, plus on upper side, negative on other. Then applying basic KVL again and VC equal to Vm. Now final output is obtained across the sum of VC1 and V2. So this is again the movement shown by a purple color line here. Here again we need to make sure that only magnitudes are taken as sign has already been taken care of when writing the KVL. So for the purple line, I have this blue shaded KVL equation minus V0 plus VC1 plus V2 equals 0. So V0 equals to VC1 plus V2 equals to twice V. So here we can see that output earlier was also obtained twice Vm, but a little drawback was there that output was of a negative sign polarity. And in here we can clearly see that output is again obtained as twice, but polarity is positive. So the disadvantage or shortcomings of hot half-wave voltage multiplier circuits has been easily overcome using this. So this is all about the brief explanation of half-wave and full-wave voltage circuits. Now, as we earlier mentioned that advanced portion of circuits also exist, which we are termed as voltage Doppler and voltage quadrupler circuits. It can also actually, as the name suggests, we can obtain thrice and four times of input on the secondary side. But even we can obtain same input twice, we input thrice and four times. So actually, this is the combination of all type of voltages till four times which can be obtained. So moving on to next slide. In the upper part, basic circuit configuration is there. Now, as we have earlier seen, that basically two capacitors and two diodes are there. So to charge all the capacitors given, for example, in the half wave and full wave voltage multiplier circuits, a complete 10-period cycle was needed, one positive half cycle and one negative half cycle. So here, if we see there are four capacitors and four diodes combination, so we can easily predict that for two diode and two capacitor systems, one complete cycle was there, one positive half, one negative. So it is obvious. In here, we will take at least two cycles. Minimum two cycles is needed to charge the capacitor C4, including C1, C2, and C3. So, in order to charge full four capacitors, two completely input cycles are taken. So, this circuit mainly is divided into two positive half cycles and two negative half cycles, which will be dealing one by one. So, in the bottom, we can clearly see we are taking first time period of input, which is shown by area 1 and area 2. So for now, positive half cycles we have taken and polarity for reference has been shown. Now let's see the behavior of all diodes and all capacitors. If we are taking diode D1, since we are taking diode D1, which is firstly connected, supply of plus and P type of diode D1 are connected, so D1 gets forward biased. In seeing D2, N of D2 is connected with plus of D2, so D2 gets off. As soon as D2 gets cut off, and D3 also gets cut off, C3 cannot be charged. As soon as D2 gets off, C2 cannot charge. So, what happens in the first area positive half cycle is that diode provides a path for capacitor C1 to charge. D2 gets off, so no path is provided to C2. D3 also gets off, so no path is provided to C3. So in a nutshell, D1 is on and all diodes are off and only C1 gets charged and all other capacitor remains uncharged. Now as shown by a red dark line, a basic KVL is applied here and voltage across VC1 is obtained equals to Vm with positive sign. So if we want to obtain output same as secondary output, we can take the output across VC1 and drive a load voltage. So in the first half cycle, we can obtain input same as on the secondary side. Now moving on to next. Since capacitor charge discharging time is kept high, so in here we can see during the first half cycle, first negative half cycle is being taken here. Now polarity is changed in reference to the area 1. Now capacitor C1 is already charged with given polarity. So this capacitor C1 gets D1 on and D2 on. As soon as D2 gets on with the external circuit Vm as given polarity, current flows through dotted line this and V2 gets charged with the given polarity. Since the current entering plate of capacitor is kept positive, so in here we can see that current current movement direction anti-clockwise. So capacitor on the left hand side is positive charge and on the right hand side was negative charge. Now the red loop we are applying the basic KVL here and putting the relevant values, we can get twice V. So you can clearly see that through this basic circuit only, which is a combination of 4 diodes and 4 capacitors, exact voltage of transformer secondary slash twice voltage has been obtained. Still, 2 capacitors are remaining to be charged, which will be used in a combination way so that thrice and 4 times voltages can be easily obtained using this. So now moving on to next half cycle, keep paying attention to the input. Now first time period has been passed and 2 capacitors C1 and C2 has been charged till now, which are shaded in here in the green section. Now next cycle begins with area 3 shown here, which is our second positive half cycle. So polarity gets again reverted. Now this plus now cannot forward bias D1 since capacitor negative plate is directly connected to it. So in spite of that this is plus here, diode D1 does not get on. In the same way, capacitor C2 negative plate is keeping cat diode from getting on. So during cycle 3, as shown in the input waveform, diode D1 and D2 is off, diode D3 gets on, which provides path for capacitor C3 to charge. It is shown in the dark red line. Now, see the negative plate of C3, which is directly connected to N type of D4. So since this capacitor C3 is still being charged, so this polarity will be finally obtained after cycle 3 has been fully vented out. So during the process of charging, as shown by dark red arrow, we will apply basic KVL and putting the relevant values. We obtained voltage VC3 equals to twice V. So in order to obtain thrice of supply, as shown in here in the purple, V0 plus and minus. So as to obtain the thrice time of supply, voltage across C1 and C3 has been combined to give the output as shown here, thrice of maximum input. So as we see, as cycles keep moving on, each capacitors get readily charged as per as diode behavior, and their time constants are so selected so that charging time is very fast and discharging time is kept very large. So there is a very less depreciation in value and a stable constant output is obtained. Now we can see clearly here, 3 capacitor has been charged till now and 3 range of half cycles have been completely used, 1, 2 and 3. So these 3 half cycles in which there are 2 positive half cycles and 1 negative half cycle has been used to charge these 3 capacitors. Now we are moving to our last capacitor C4, which is shown in input in the bright yellow spot. Secondary side polarities are again reversed. We can clearly see the charge retentivity is being maintained during even this area 4 cycle, which means what assumptions we have taken that discharging times should be large enough. The reason being these discharging times to be large enough was that so as to retain the charge. Elsewise, there will be a slope and our whole purpose of getting a constant output will not be fulfilled. So as you can clearly see, C1 sine plates is keeping D1 off. C2 sine plates is getting D2 off, and now C3 negative plate is keeping D3 off. So with the external polarity as shown here, plus of this is directly connected to p-type of D4. Hence, this red line shows the current flowing direction which flows through C4 and get bypassed over D1, D2, and D3. Now applying basic KVL in the red loop, we obtained here VC4 equals to twice V. But as the circuit suggests, using this circuit we can use thrice and 4 times of voltage on the secondary side. So we have to see how we will obtain this, which is shown here in the green line. See this, the output here we have taken across C2 and C4. Now carefully watch. Thus voltage across C4 and C2 has been clearly matched with the output polarity. Elsewise, there will be cancellation in voltages values. So utilizing C2 and C4, we are obtained here voltage across V0, which is eventually taken across capacitor C2 and Q4, which combination gives output voltage for 4 times of basic supply. So going through all the cycles, we can clearly see that in a mid-range, now this basically these circuits cannot be used to produce very high voltages ranges like 1000 volts or 2 kilovolt, because one thing is there, power transmission needs a transformer primarily through passive components like KCL. Such high power cannot be made to move. And secondly, we are working in a mid-range around 55 to 60, 65 volts variation. For example, in your mobile chargers, some old ones, we can see there was a knob through which we can select the various step voltages. So this is primarily just a thing like that. When the combinations are selected, which means the regulator is moved to the position such that eventually what capacitor needs to be included here gets included. So this basically produces a variable supply. Now, this is a lot different from rectifier circuits, because rectifier circuits generally based on filtrations and such. Well, these circuits, no filtrations are used, and basically diodes and capacitors are used only. So this system gets lightweighted and easily to use. No extra requirement of heat sinks and things like that, which are needed in rectifier and voltage regulator IC systems. So as earlier I have said, not very large range can be manipulated using it, yes, but mid-range can be done. So hopefully this session has cleared your doubts regarding the voltage multiplier systems. And in the forthcoming sections, we will see the clipper and clamper circuits and the basic working of Zener regulators. Thank you for watching. Thank you very much.